Hey everyone, just wanted to welcome you to Lab 2 for ME124. This lab will be looking at beam bending and vibrations, and we're going to be introducing strain gauges. So as far as the technology in the lab today, we're going to have strain gauges and some data acquisition systems. The theory that we're going to be taking a look at in lecture today is beam deflection during bending, normal strain during bending, vibration analysis, and prediction of elastic modulus. Shown here in the slide, we have a cantilevered beam clamped to the edge of a workbench here. You can see our C-clamps holding it down, steel plate on top of it. So it's clamped right here, cantilevered out off the bench. And we can see right here and here, we have two strain gauges attached to our cantilever beam. So here's a little bit of a close-up. Again, here's that same strain gauge. Now we can clearly see our two leads that are soldered onto that point right there. So here in this slide, we can see off the left over here, we have a set of weights. We can clearly see each of these weights is labeled. We'll be hanging these weights off the end of this cantilever beam over here, and we'll be measuring the deflection of the beam with this gauge right here. Now there are a lot of different types of strain gauges. We'll be using, you can see in the top left here, the linear strain gauges, as you just saw in the previous slide. We also have some double linear, single shear, double shear, T-rosettes, half bridge, full bridge, and membrane rosettes. For different applications, we may want to utilize different strain gauges. So on this page here, we can see some of the applications and uses of strain gauges: sports equipment, motors, bridges, supports, structural. Reason we utilize strain gauges, they're relatively rugged and stable, widely acceptable technology, cheap to purchase, and a lot of the load cells that we'll actually be using, these are the basis of how those are comprised. So looking at the breakdown of an actual strain gauge here, we can see you have the backing, encapsulation, you have your copper coated tabs that we'll solder on our leads, and we have alignment marks as well. So this is very similar to the strain gauge you're going to be using in lab today, referring to the different components of this as mentioned here. So basic principle, we can use strain gauges for both tension and for compression. Now in tension, the length is going to increase, the area of the wire is going to decrease, and therefore your resistance is going to increase. Now the converse of that here, for compression, the length is going to shorten, the area thickens, therefore resistance decreases. So we can see that illustrated over here on the right. You have tension in the center here, compression on the bottom there. So as we mentioned, we're going to experience lengthening under tension, and when we deal with that, we'll also be looking at Poisson's effect and using some equations and calculations for that. So key equation here, we have electrical resistance in a conductor. So we have this equation right here. R is equal to rho L over A, where R is our resistance in ohms, rho is our resistivity. You can take that right from an ohm meter in the lab. L is the length given in units of meters, and A is the cross-sectional area. So you can plug all those values into this equation up here, and we can use this to calculate whatever the unknown is. In this case here, we have it set up to calculate the resistance. So if we wanted to find out how resistance changes with the length change, we can use the same equation we had in the previous slide here with a couple manipulations to it. Take the log of R, this will be equal to the log of rho plus the log of L minus the log of A, where for our area here we can plug in our values. So the log of R is equal to the log of rho plus the log of L minus the log of pi plus 2 times the log of R. Then, if we were to differentiate, what we end up with is dr over r is equal to d rho over rho plus dl over l minus 2 dr over r, and this will give us the resistance change with the change in length. So we mentioned that we want to take a look at Poisson's effect. So we'll take a look at our governing equation here. Epsilon sub t is equal to dr over r is equal to negative v times dl over l. Now we notice that this dr over r appeared at the equation from our previous slide for change in resistance with change in length. So dr over r is equal to d rho over rho plus dl over l plus 2 times dr over r. So now we can sub in this relationship here into our dr over r and this. When we do that, we end up with this expression over here on the right, d rho over rho plus dl over l minus 2 times negative v times dl over L. We can reduce this down a little bit, and we see we have d rho over rho plus dl over L times 1 plus 2v, which is also equal to d rho over rho plus our epsilon here times 1 plus 2v. So let's take a look at our gauge factor for the change in length. So we have this relationship here, F is equal to our delta R over R divided by delta L over L, where we can take a look at this, and our delta L over L is our epsilon value here. We can reduce and plug that in. And we have now, if we rearrange this here, solve for delta R over R, we have that delta R over R is equal to F times our epsilon, where we'd solve for our delta R over R or dr over R on our previous slide there, so we can plug in that relationship right here now for our delta R over R. We're left with this here. We can reduce that down. When we do that, we end up with F is equal to 1 plus our 2V. So look at our strain gauge again here. Talk about transverse sensitivity. So a couple items here. Not a single wire. Ends and sides will experience transverse strain. And alignment off the principal strain axis will result in transverse strain. We can see here we have our relationship that we just saw from the previous slide. Our delta R over R is equal to F times our epsilon. So let's take a look at transverse sensitivity. So for a real strain gauge, it has two factors here. So we have this following relationship here. We have delta R over R is equal to F sub A times epsilon plus F sub T times epsilon T, where our epsilons are the strains parallel and perpendicular to the gauge axis or the grid lines in the gauge. Our F sub A is our axial gauge factor, and our F sub T is our transverse gauge factor. So if we define our transverse gauge or transverse sensitivity, we have that K sub T is equal to F sub T over F sub A, where K sub T is our transverse sensitivity coefficient, referred to from here on out as the transverse sensitivity. So for Poisson's ratio, we can plug in here. So now our delta R over R becomes F sub A times our epsilon plus K sub T times epsilon sub T, which is equal to our F sub A times epsilon minus K sub T V times our epsilon. It's also equal to F sub A times 1 minus K sub T V with our epsilon pulled outside there. So just a simplification by plugging in from Poisson's ratio into our delta R over R equation. Now our gauge factor accounting for transverse sensitivity now becomes that F is equal to FA times 1 minus K sub T times V. Now if we take a look, there's a note down here, only for when it is calibrated, and V is equal to 0.285. So shown here, we have some general information on the strain gauges that we'll be using in the lab. So these are from Micro Measurements Division group here. So we can take a look. They give us some information on the chart, gauge type, and some more information there. Great thing to reference when you're using any strain gauge is the manufacturer's documentation, any calibration factors, anything that they have that they've tested beforehand. Great to have that so you know what to plug in for your equations. So shown here is some of the equipment we'll be utilizing in Lab 2. This is the strain gauge amplifier. So it's a little bit older one, the P3500 here, but it works perfectly for what we're doing. It plugs right into our strain gauges. If you take a look inside the top, it gives you a little bit of instructions of how to use, what to connect the wires for quarter bridge, half bridge, full bridge. So this information is right there underneath the top lid of our amplifier. So now let's take a look at our quarter bridge or our Wheatstone bridge circuitry. So up here we have our circuit drawn out on the top left here for our Wheatstone bridge. We have our voltage VI coming in here. We have our resistance going around here, V naught there, and we have our R plus delta R for our strain gauge there. So this is our circuitry diagram for a Wheatstone bridge. Now for an unstrained circuit, the bridge is balanced, so our delta R is equal to R, and our V naught is equal to 0. But under an applied strain or loading, our delta R cannot be equal to 0, and our V naught is not equal to 0 there. So we have this relationship here that we have our V naught over VI is equal to our delta R over R plus 4 plus 2 over delta R over R. Now, if we were to replace our delta R over R with our F sub epsilon, we have the following relationship shown here. Our V naught over VI is equal to F sub epsilon divided by 4 plus 2 times F sub epsilon, which is going to be nonlinear. And we can show down here our deviation from linearity in this following plot here. On this plot here, we have our strain, our epsilon on the x-axis, our origin right here, and our y-axis, we have V naught over VI. So with this lab, we're going to need to record some data from our strain gauges and our strain gauge amplifier, and we'll do this with some data acquisition equipment here. So some of the pieces of equipment that we're going to need here are you're going to need your laptop, portable computer, analog to digital converter, USB cable, software interface, which should be loaded on the portable computer here with National Instruments running our DAQ there, and another way we could do it is with a data logger or an Arduino. So if we don't have a laptop loaded with all this software here, we could easily program several different types of data loggers that are out there that are standalone options that we could plug right into our strain gauge, and a Arduino can be programmed as well to accept and record the data. So here's an example of kind of one of these standalone units right here. So here's a National Instruments DATAC right here. So this is the NI USB 6008. Has a certain number of inputs that are allowed. We can see over here on the sides of this here, some digital, some analog. Things to look for is what is the speed acquisition? How many samples per second is this system capable of, and how many are necessary for our experiment? And that's going to go along with our resolution. What resolution are we looking for? Bits per sample and the speed of the counter on this. So these are all things to consider when we're speccing out a data acquisition system. National Instruments does have a lot of these, but there are some other competitors that have cheaper options that have free software as well. So they may be a little bit better for some experiments where you don't have a large budget or don't want to program in an entire data acquisition system. So now let's take a look at our beam deflection under a point load. We can see here at point B, our x is equal to 0. So we're starting at B here. Our x starts at 0 and moves out in this direction there. Along the x-axis, we have a beam of total length of L. We have some external load P applied here at the end at point A. And we have some V sub A here for the velocity of point A going down here. We have a moment M sub B about point B there. So from this here, we can draw out our free body diagram that we can see on the left over here. And from this free body diagram, we can then come up with our moments equations. So we can do our summation of moments about point A and point B, and we can come up with these two different equations here. M plus MB minus our VB times x is equal to 0. Or from the other end, M plus our PL minus PX is equal to 0 there. So we can combine and say M of x is equal to our PX minus PL. And right here we can see our graph there for our moment diagram. So if we recall back from ME14, we take a look at the flexure formula here. The basic differential equation for the deflection curve of a beam is given by d squared v over dx squared equal to mx over ei, where we have the moment of inertia, our I value here for a rectangular beam that we can look up is I is equal to bh cubed over 12. So we can plug that back in to this equation up top for our I. So for our point load here, we have a basic differential equation again right there. D squared v over dx squared is equal to mx over our ei. Point load, we have mx is equal to px minus pl. Integrate it twice, and we can obtain beam deflection delta. So our delta x is given by this relationship down here. After we got a little bit of calculus, delta of x is equal to p over 6 ei times x cubed minus 3lx squared. So here we have the plot shown below for determination of E. So if we want to plot the maximum deflection, our delta max, versus our load P. And we can see here's our load P on our x-axis here, and our negative delta max on our y-axis over here. So we have this relationship here that our delta max is going to be equal to our delta, where x is equal to L, or this is equal to a negative PL cubed over 3EI. So now looking back at our flexure formula here, we have our normal stress distribution due to M, our moment here. So we have the sigma is equal to negative my over I, and we can see our variables down here in the diagram below. We have our y-axis right here on the edge there. We have our sigma max, our sigma here, at some distance y off of our x-axis right here, and there's our moment going right there. So another relationship we want to talk about when dealing with normal stress here is Hooke's law. So in part 2 of the lab, the strain gauge measures the maximum normal strain. So we have our relationship here for strain. Strain is equal to our negative y over c times our epsilon max. And our stress right here, our sigma, is equal to negative y over c times our sigma max there. We have our corresponding diagrams down below for stress and strain. So approach 2 for the determination of our E is we can plot the maximum strain from the gauge versus our load P there. So now we have our relationship here that our sigma max is equal to negative MC over I. We have the relationship here that M of x is equal to Px minus PL that we saw for earlier. This yields that we have our epsilon max is equal to sigma max over E. We can plug into that is now P times our x naught minus L times C over our E sub I right there. So then we can plot this here with our x-axis being our load P and our y-axis being our epsilon max. So start talking about vibration here. If we're talking about free vibration, we have to consider our natural frequency right here. So we have a fixed point over here, a beam, and a free end of our beam over here. And if we graph our amplitude versus time, we have something down like we see down the bottom here, where we have our sine right here. So amplitude changing with respect to time, and from peak to peak right here we have our period. So for our beam, we can define forces and moments on length dx. So down here we can see in our little diagram here, here's our dx right there. So along this length dx here, we can see we have our shear, our V right there, and our shear on this side over here now, our V plus our delta V right there. We have a moment over here and a moment on this side of M plus dm right there, where if we look here, density is going to be a rho, area is our A, modulus is our E, and our moment of inertia is given by the variable I. So now let's take a look at the vertical equilibrium for our beam here. For this beam, we have our diagram over here, our dx, our moments, our shears, and what we can see here is we take the summation of force in the y direction equal to MAY from Newton's second law, we can derive the following equations here. So our delta V, delta x, our partial of our shear with respect to x, negative dx, is equal to our rho a dx times the second partial derivative of u with respect to t, or delta squared u over dt squared here. And we can reduce this down. So partial of v with respect to x negative is equal to rho a times delta squared u over dt squared, or the second derivative of the partial of u with respect to t. So we have that relationship down here now from our diagram in Newton's second law. So now we can take a look at our beam flexural equation here. So we have a relationship here. The m of x is equal to EI times our delta squared u over dx squared. Now we can take the derivative of that. Our partial of m with respect to x here, our delta m over delta x, is equal to now EI times delta cubed u over dx cubed. And we can go one step further here and take the second derivative with respect to x of our m here. We end up with E sub I delta the fourth u over dx to the fourth. So from our shear moment relationship here, we have V of x, or shear of x, is equal to our partial of our moment with respect to x. So dv dx, take the derivative of that, is equal to delta squared m over dx squared. We can rewrite this as negative delta v over dx equal to rho a times delta squared u over dt squared. Combine this here, and we have delta squared m over dx squared is equal to rho a delta squared u over dt squared. So our delta squared m over dx squared is equal to our ei delta to the fourth over u dx to the fourth. And we finally end up down here now, their last relationship here, negative ei delta to the fourth u over dx4 is equal to our rho a times delta squared u over dt squared when we combine everything. So if we were to rewrite these equations here, we have the following relationship here. So we start off with the same negative ei delta fourth u over dx squared reduces down to rho a, or equal to rho a delta squared u dt squared. Go down through some simplifications here, and we end up with down at the bottom this following relationship boxed in here, which is a fourth order partial differential equation. You can see there's our fourth order right there, and our deltas right here make this a partial differential equation. So a diagram here for a couple different scenarios. Here you have this cantilevered beam coming off the end of a fixed point over here, some total length L over here. So we have our relationship given by the equation omega sub n is equal to alpha L squared times the square root of EI over rho A L to the fourth. So then we have our omega sub 1, omega sub 2, and omega sub 3 for those frequencies. So that's A, B, C, and D here with the corresponding omegas. So talk about damping now. Like all the systems that we dealt with before, there's still going to be damping here. So we have this x of t plot here showing our damping for our cantilevered beam. So exponential envelope around a periodic isolations. We have this following relationship here for x of t, where our omega sub n is our undamped natural frequency, our omega sub d is our damped natural frequency, and we have our damping ratio as well. So if we're talking about damping now, we have a relationship among our different variables here. So our omega sub n, our undamped natural frequency, our omega d, our damped natural frequency, and our damping ratio, we have this following relationship here that omega sub d is equal to our omega sub n times the square root of 1 minus our damping ratio squared right there. So from that there, we can reduce this down for our f. Our f is equal to our f damped divided by the square root of 1 minus our damping ratio squared. So let's talk now about our logarithmic decrement method. So this is a method used to find the damping ratio of an underdamped system in the time domain. So it's very specific. It's an underdamped system in the time domain. And the logarithmic decrement is the natural log of the amplitudes of any two successive peaks. So we'll utilize this plot here to relate to our equation where we have time going across this axis right here, and our values for x up here on this axis here, and we have our relationship here for our ratio, our damping ratio here, we have 1 over 2 pi times, on the numerator up here, we have this relationship here, 1 over n minus 1 times the natural log of v L over Vn. We can see there's our VL right there, there's our Vn right there from our plot above, all over our denominator here, which is the square root of 4 pi squared plus 1 over n minus 1 times the natural log of VL over Vn quantity squared.